So part one of lab number 6, examples of chemical reactions. The very first thing we want to do is do a little bit of technique on how to light your Bunsen burner. And so whenever we do this, we want to be able to turn on our gas source. We have this open. And so if we take our striker, and we don't have to have a flame, but this thing is striking. Oh, and what we notice is this has got a little too much gas going on there to strike very well. So the other part is, if this doesn't strike in the first few seconds, notice you're probably putting propane into the air and it is going to explode, which is going to be dangerous. So we would shut this off immediately. So if we got this situation where it is way too high, yeah, you can get that flame going and bring it down. But the safest way to do this is you've probably got too much oxygen. And so we're going to bring down the amount of oxygen. Okay, try this again. And then we can adjust. We don't want this yellow flame at the top, okay? We want to have a nice blue flame. So we're going to pull this or turn this so that we do have more oxygen, to where it just has the inner blue flame nice and distinct. We can turn down the amount of gas over here, or in this type, we can change the amount of gas this way and bring that down a little bit as well. Okay, maybe not as much. So there we go. So this is the burning of propane. And so propane is C3H8. And for a combustion reaction, we have to be combining this with oxygen in the air. And so what is the products that are going to be coming out of here? It's obviously not liquid water, is it? So go ahead and complete your portion, and we'll go on to step 2. So part two, we're going to take this magnesium metal. It has oxidized a bit over the days. It does have this darker stuff. I've sanded it off so you can get some of the color of the metal. It is a gray, shiny metal. It is fairly soft, but we're going to heat this up so that it can overcome the activation energy and really react with the oxygen in the air. And so once we get this hot enough, it's going to sustain itself, but we will not want to look directly at this, and it's going to be hot, so we don't want to let it drop on the table either. And so we're going to hold this over the top of the porcelain crucible, not a crucible, I'm sorry. It is the evaporating dish. But once we get that started right there, we're going to hold that. Notice how bright it is on the camera. I'm not looking directly at it, just kind of out of the side of my goggles. And so we've got this white powder. And so the magnesium metal has combined very quickly with the oxygen in the air. So you can do the balanced chemical equation of that and record that in your lab. Part 3 of the lab. What we have here is about 10 milliliters of the 6 molar hydrochloric acid solution. So we definitely will be wearing goggles, and we're going to make sure we didn't get this on us when we measure this out. Make sure we clean it up immediately. And then we're going to, again, put just a little bit of this magnesium into the hydrochloric acids. So this is going to be a replacement reaction. We've done this as a demonstration before in class, and so now this is part of the actual lab. And as this is a double replacement reaction, it's going to give off a gas. It's going to bubble. And so what type of gas is going to occur here? You've got the aqueous HCl, and you've got the magnesium metal, and so the magnesium is going to dissolve, and so it's going to be aqueous magnesium, and so it's not going to be in metallic form with metallic bonds, so it's going to be an ion at that point, dissolved. And so we need to know what type of reaction it is, what is being given off, so we can balance the chemical reaction. And so a second reaction is going to occur so we can prove what type of gas is being created. And so we're going to make sure it's not carbon dioxide gas, it is not oxygen gas, but it is the other type. Come on, get in there. So that did not go as planned. So we're going to start this again. So we're going to put this magnesium into the hydrochloric acid. Have a very vigorous reaction here. This may not work as well if we created too much water vapor and displaced this material, but it does happen very quickly. So I'm going to take my wooden splint here to the bottom of this gas that we have collected from the top. And again, we have a confirmation that that was hydrogen gas that was collected when it was created. Hydrogen gas was very light, so it went up into the collection chamber, and then we lit the mat or the wooden splint, went down here. Any of the oxygen from the atmosphere, which may have been in the test tube, mixed with the hydrogen gas, and then there was another combination reaction there, and we can see that that hydrogen and oxygen created a nice fog or bits of condensation on this cool glass. Part 4. We have a replacement of copper by aluminum. And so we're going to start with the copper nitrate, which is dissolved into the liquid here. We're going to take our aluminum foil, which I have crumpled up so that will fit into the test tube. We're going to put it in there. We're going to use our glass stirring rod to get this immersed. Now the aluminum foil, it does take a little while to get started because it probably has a aluminum oxide coating. Once it does, notice there's going to be some bubbles. The reason that it's bubbling is because this is an exothermic reaction. It is hot. So what you're seeing there mostly is the heating of the water, so that it actually is so hot it is boiling that water at the surface of this reaction. So we may be seeing the color change, this brownish color. It looks like the aluminum's turning brown. It's not. That is the copper metal forming at that surface where that chemical interaction is occurring. And so the copper, which was dissolved as copper 2+ aqueous into the liquid, is now the solid, as any of that aluminum, which was a solid metal with metallic bonds, has now been dissolved and is now an aluminum Al3+ aqueous. And so now we have aluminum nitrate in this solution, which we will have to dispose of appropriately. And so notice, if we let this settle for a while, and we can, then the color is not nearly as blue. And it's nice and dark because of all of the tiny, tiny bits of copper that are being suspended at the moment. So we will let this settle for a while, and we'll come back and look at the color again. So after several minutes, it has settled down just a little bit. But what I want to show you and kind of zoom in is the color of our test tube has really gotten a lot lighter. I don't know if you can see that. The solid copper settled to the bottom. Now it is still having a tinge of blue. That means that some of the copper nitrate is still in there. Some of the copper is still there. But if we looked at aluminum nitrate, it's going to be a clear liquid if it was pure aluminum nitrate. And so the disappearance of the blue does indicate that some of the copper is still left. But because it is such a light blue, not nearly as much. And so if we wanted to do the math, we could have figured out just how much aluminum by mass that we could have used to get rid of all of it, and have an excess of aluminum to ensure that all of the copper was done. or we could have made sure that there were no parts of aluminum remaining based on the stoichiometry. So that would have been fun. Part 5, decomposition of hydrogen peroxide. We're going to use a 6% solution of hydrogen peroxide. Just to give you a reference, the hydrogen peroxide that you get at the pharmacy or an apothecary is going to be about 3%. I don't know if you can see that or not. So 3%. So this is twice as concentrated. This we know does a good job. This might actually cause a little bit of extra harm to your skin if you get too much on it. So that's why we're going to be extra careful with it. Definitely wear our goggles. And you'll notice it even has a little tiny pressure hole as this decomposes. This is put into light-proof bottles. So when you buy this off the shelf, these are all never going to come in the clear bottles like an alcohol does, because the UV light or just light itself will actually help stimulate or overcome the activation energy so that this stuff decomposes on its own. So we're going to speed this decomposition up very quickly. So this is H2O2. We're going to put a catalyst in it of manganese, not magnesium, but manganese dioxide. And yes, I used the rolling method to get this material out. So this is decomposing. This is about 15 milliliters of the 6% hydrogen peroxide solution. And so this is decomposing right now. You can see the tiny little bubbles if you were here. But we're going to put this material in here, and it's going to decompose quite a bit faster. And so as we look at the bubbles that form, how do we prove which type of bubble this is? What type of gas is being evolved? Is it going to be hydrogen gas that explodes, or is it going to be oxygen gas? Well, we kind of know what this is. So we're going to see the bubbling action. Now, yeah, it turns nice and gray, but most of that is because that is the manganese dioxide that is floating around in there in tiny little bits. So what we have here is this ember. Let me get this just down to a glowing ember, just to coals. If I put this back in here, that's oxygen. It will increase the rate of the combustion of that wood, and you'll notice it gets really bright when you get closer. So if I blow that out, very flammable piece of wood today. So notice as the concentration of oxygen increases, been nice to have done a kinetics experiments with this, right? Concentration and reaction rates. Well, my gosh. So every time we can get this to relight, that's the beauty of using the 6% hydrogen peroxide. It continues to decompose a lot longer, and so we can continually do this over and over again. Whenever this would be finished, all of this manganese dioxide would settle to the bottom. It would be clear water again, and all of the oxygen would be gone. And so what you would have left over is this manganese dioxide, and we can use it over and over and over again. But it's cheap as dirt, so we just kind of throw this into the trash, and that's what we do. So part 6 of 6 parts. We've got a few more than just 10 milliliters. We have 0.1 molarity silver nitrate. If you wanted to do some research, you could actually see what concentration maybe they used to use of the silver nitrate and maybe put in babies' eyes in developing countries to get rid of certain types of bacterial infections, or to prevent bacterial infections in the eyes of newborn babies. Don't think that's done in the United States anymore, but it used to be years and years ago. So we've talked a little bit about the bacterial properties of silver before, and even how the pioneers would use it. But anyway, this is in a silver nitrate form, and we've got some copper chloride. And so if you consult a table of solubilities, and so the solubility tables, we're going to see which, silver nitrate, all nitrates are soluble, and copper 2+ with chlorides are soluble. So if this is a double replacement reaction, we can end up with a silver and a chloride. Is that what is going to be insoluble, or is it the copper nitrate? Well, we know that copper nitrates, anything that's a nitrate is going to be soluble. So we're going to take just a little bit of this. We're going to add it to the silver nitrate. And we've got this solid that is being formed. That is a precipitate. Maybe you can see a little bit better there. So that white solid that is being formed, what is that material? And then you need to balance your chemical reaction. Make sure that you understand that this white material is a solid, okay? And we could continually add this until this material, this liquid turns blue. That means we've used up every bit of the silver. And so that if it stays blue, then we know that some of the copper chloride is still in solution. And so we could even test and make sure using stoichiometry and how much we've used, if we were measuring these amounts, if our molarities were correct. So notice this is all falling to the bottom. If we wanted to filter this material out, if we thought this was important, we could filter it, rinse it with water because it's insoluble in water, and then we could obtain that material itself if that was important for us. Part 6. Make sure you put all of this into the Google Forms that goes right along with all of the parts of the lab in the Google Classroom that is assigned to you, and that's what will be graded.